The human-machine interface of an intraluminal robot is the interface used to maneuver the endoscope, together with the adopted control strategy and the quality of feedbacks received during the intervention. It has a crucial impact on the clinician's performance, since it can increase or decrease the difficulty of the task, and it is strictly connected to the user's physical and mental stress. So this paper presents the first framework up to compare and evaluate different human-machine interfaces for robot colonoscopy to identify the optimal interface that minimizes the clinician's efforts and maximizes the clinical outcome. The framework comprises, first, a virtual simulator of the intraluminal procedure, in this case is robot colonoscopy, that serves as an open and safe and controlled platform to test the different interfaces. The simulator was clinically validated by 28 clinicians and includes 3D reconstructed anatomies from CT colonography images, realistic deformation of the tissue due to the contact with the endoscope, and realistic visual rendering. The framework also includes wearable sensors measuring the user's cognitive load while testing the devices, a data collection unit of metrics correlated with the clinical performances, such as the force exerted on the colon walls or the percentage of mucosa visualized, and finally, questionnaire exploring the user's impression and perceived stress. The framework was tested with 42 clinicians investigating the optimal device for teleoperated control of robotic colonoscopes. 2 control devices were selected after a preliminary survey and were compared. First, an haptic serial kinematic device, and second, a standard video game joypad. The results showed that the haptic device was preferred by the endoscopist, but the video game joypad objectively enabled better clinical performance and reduced the cognitive and physical load of the user. So this framework can be used to evaluate different aspects of a human-machine interface, both hardware and software, and determine the optimal interface that can reduce the burden of the clinician while improving the clinical outcome. The findings of this study and of future studies performed with this framework can inform the design and development of the next generation human-machine interfaces for intraluminal robots, leading to improved clinical performances, reduced physical and mental stress for the clinicians, and ultimately also to better patient outcomes.